Today, we're breaking down rectified linear unit, also known as ReLU, one of the simplest but most important activation functions in deep learning. The formula is max of 0 and x. Negative values get cut down to 0 while positive values pass through unchanged. On the graph, you can see how it stays flat for negatives and climbs linearly for positives. So why does this function matter so much? ReLU keeps positive signals and kills negatives, and makes networks sparse and efficient. It gets rid of the vanishing gradient problem and is computationally cheap, and is also one of the reasons that deep neural networks became practical to train. The catch? If too many neurons keep outputting 0, they can stop learning completely. This is known as the dying ReLU problem, which I'll get into in another video. Now, let's walk through a tiny example with one node that has 2 inputs and 1 output. We'll label the inputs x1 and x2, and the weights w1 and w2, and then we'll add the bias. So first, we calculate the weighted sum. So z equals w1 times x1 plus w2 times x2 plus b, the bias, which is just the dot product plus the bias term. Then we apply the ReLU activation. If z is negative, the output is 0. If it's positive, it just passes through. So plugging in the numbers, x1 equals 2, x2 equals -3, w1 equals 0.5, w2 equals 1, and b equals 1. That gives us v equals -1. After ReLU, the output is 0. For this example, this means that the node is not activated, so it doesn't contribute to the network's decision. So when this node outputs 0, it stays silent and no signal moves forward. That's fine in small doses, but if too many neurons keep going dark, your network stops learning. That's the balance ReLU brings. It's simple, efficient, but not without risk. I'll talk about ways to fix this in a different video, but if you found this helpful, hit like and follow for more clear, bite-sized AI breakdowns.